Thanks. I'll begin with a word of prayer. Heavenly Father, we thank you for this day. I thank you for these students. Pray that you'd just bless this time. Help us to glorify you again, Lord, what we do. In your name I pray, Lord Jesus. Amen. Are there any seaflowers in here? We were spared the seaflaw. I had one seaflower in abstract algebra. Wait a minute. Were you here before? Okay. We're glad that was believable. Let's hear. Oh, goodness. I don't know. I'm not sure I'm here. All right. Differential equations. So let's look at another application. Newton's law of cooling. It states the following: dt is equal to something like k times t minus r. I mean, different books may put r minus t and make k positive or negative. It's something like this, though. Now here, this is the room temperature. Does that make sense? So it says that the rate of change, what this is describing is the temperature in some object, like the cup of coffee I should have had before class, for example. So you got some temperature, right? And then out here you've got room temperature. And so, of course, as time goes on, what happens is the heat, the collective kinetic energy of the coffee molecules, and they vibrate around, and then they hit air particles and so forth, and they lose energy, and eventually everything assumes room temperature, right? So what this equation says is that the change in temperature of the coffee is proportional to the difference in the temperature of the coffee and the room temperature. This is Newton's law of cooling. Now, so let's see here. For example, we could say find the temperature at time t for coffee given room temperature is, say, I don't know, 70 degrees. We'll use Fahrenheit. We're civilized people. We don't use centigrade. Let's see here. Sorry. Temperature 70 degrees Fahrenheit. And the initial temperature of the coffee is equal to, let's say, 140 degrees Fahrenheit. But after 1 minute, the coffee has cooled to 120 degrees Fahrenheit. So I think given all this data, we can figure out what the temperature in the coffee is at time t using Newton's law of cooling. All right? So let's see, let's try to work that out. So first of all, what's my differential equation? I've got dt is equal to k. I don't know the k yet. And then t minus and minus 70, right? 70 is the room temperature. So that's my starting point. How do you guys want to solve this? We got two. I'm gonna do integrating factor technique this time. You could use separation of variables here if you liked. This is one of those ones you could either use separation of variables or integrating factor technique. It's like the RL circuit, much the same kind of animal. So what's my integrating factor? My p, the coefficient of t, is minus k. So I do integrate minus k dt. So I have e to the minus kt as an integrating factor. And then I think I need a battery. So multiply star by the integrating factor. What's that give us? E to the minus kt times dt dt minus k e to the minus kt t equals to minus 70 k e to the minus kt. But by reverse product rule, we have ddt of e to the minus kt times t is equal to minus 70k e to the minus kt. Right? Let's see here. Now integrate both sides with respect to time. And we get e to the minus kt times the temperature function is equal to, let's see, when I integrate this, 70k is just a constant. So I've got like minus 70k. Then I have to divide by minus k because I'm integrating e to the minus kt. So basically I'm making a u equals minus kt substitution. Then plus a constant, right? The k's cancel, the minuses cancel. We have e to the minus kt times big T equals to 70 e to the minus kt plus c. So you can solve that for t. We get t of t is what? 70 plus c times e to the kt. All I've multiply both sides by e to the kt. It's cool. So all I've used so far is that the room temperature is 70 degrees, right? I have not used the data that the temperature at time 0 was 140 or the temperature after 1 minute was 120, right? So now I apply that data and see if we can figure out. See, there's two constants in here, right? There's the c and the k. So t of 0 is 70 plus c, which is otherwise known as 140. Therefore, c is 70, right? So now t of 1 is equal to 70 plus 70 times e to the k times 1, or e to the k. And that's all equal to, what did I say, 120? Let's see here. So that gives me 70 e to the k is equal to 50, or e to the k is equal to 5/7. So apparently, k is the natural log of 5/7. And so I conclude that t of t is equal to 70 plus 70 e to the k, which was what? K was natural log of 5/7 times t. Now I could I could leave like the answer like that. It seems lazy to me to leave the answer like that. We can improve a little bit. That's, I mean, a couple things here. This is 70 times 1 plus what? Plus the exponential of the natural log of 5/7 to the what? To the t power. factoring out the 70 using my laws of exponents. So I can actually rewrite this solution as 70 times 1 plus 5/7 to the t power. I know I can't usually do that kind of thing with this problem. That's just kind of a quirk of this example I made up. If you look at solutions in the past I've written for these problems, I don't usually have something like this happen. Something snazzy about these numbers I chose. But this makes sense, right? As time goes to infinity, what happens? Temperature of the coffee goes to? Yeah, 0. When is the coffee cooled off to like 100 degrees? How would you figure that out? If you wanted to figure out when the coffee is cooled to 100 degrees, maybe you like to drink your coffee 100 degrees, I don't know. I have no sense of it. Then you'd have to solve this, right? So you'd solve 1 plus 5/7 times t is equal to 100/70, you know? So that would give you 5/7 times t is equal to, let's see here, 30/70ths, is that right? Yeah. And then take the natural log of both sides. We get 5/7. The natural log of 5/7 times t is equal to the natural log of 3/7. So you get t is equal to the log of 3/7 divided by the log of 5/7, whenever that is. Or if it makes you feel better, log 3 minus log 7. Although I don't see how this is really that much better. Log 5 minus log 7, but for the love of properties of log, I'll write that out. Any questions? So this is, I mean, mathematically it's kind of interesting if you think about what we did, because when we solve this, right, this k is a parameter, right? And so we've actually solved not just one differential equation, but a whole family of them all at once. That's kind of neat, right? And that's why we need more than one piece of data here. We needed 2 conditions in order to fix the specific temperature function for the coffee, right? In fact, if you look at this generic thing, I have 1 and 2. I have 2 parameters, right? I've got the coupling coefficient of the system, as well as the ambient temperature. So I need those 2 pieces of data, as well as an initial temperature for the coffee. I need 3 independent pieces of data in order to actually apply Newton's law of cooling to a specific physical problem. You know, there's something else you could do. This would be kind of fun, though. You could take a cup of coffee, right? And you could study how its temperature changes, right? Suppose you didn't know room temperature. You could solve this with R being a variable, right? You could do that also. And if you did that, you could then look at how the temperature of the coffee changes over 3 periods. Sure, why not? Over 3 periods of time. And if you looked at that, you could then cipher what the room temperature was just from how the coffee cooled over 3 periods of time. I think that's a very delicious form of a thermometer, but you know, it's also a lot of work. So I guess we'll stick with the traditional mercury deal. Yeah, let's not think about it. I can tell the temperature of coffee from the way it hits my tongue. Like that's my ninja skill. It's accurate sensing of, but I for some reason can't, only coffee. Not room temperature, but only coffee. Yeah. Just there's something mystical about the temperature of coffee that allows me to sense it that I can't sense. Now, if you had a room full of coffee, I could sense the room temperature then. But other than that, fine, real world. It's like the discussions we used to get in my physics professor at the community college. How did we get in the middle of the room that has no friction? You know, how did we get there to start with? We don't understand how we got there, David. Never got a convincing answer. We still have to solve the problems, though. All right, orthogonal trajectories. This is our final topic for this week. So given a family of curves, you know, say that they're defined by something like f of x comma y, use big F, equals to a constant, right? So different constants give members of the family. How to find corresponding family G of xy equals to C. I'll use B, fine. So this time, this different values, you know, give, you know, curves in here, which meets, I need to give this a name. We call this one Pac-Man, which meets the Pac-Man family. In perpendicular sense. All right, so let's start out with something. Best thing I can do is show you an example to make this sort of more precise. The easiest family I could think of are these ones. So here I'm looking at f of x comma y equals to what? Equals to y equals to a constant, right? So the different constant gives you the different y levels, literally horizontal lines. So the orthogonal trajectories to these are what? Vertical lines, right? Those are the lines which meet these perpendicularly. So that would be g of x comma y equal to x equal to various choices of that constant would give you, as b varies, we get different vertical lines, right? These are called level curves. Level curves are defined by an equation, not by a function necessarily, right? Like circles are level curves. Okay, so how about this? We don't need differential equations to do this one, right? This is just common sense, right? But how about something like x squared minus y squared equals to c, defines family. I'll say Pac-Man again. Find the orthogonal trajectories of the Pac-Man family. Here's how we do it. So, first of all, this family of curves must appear as a solution to some differential equation. Let's find out what it is. So, if we have x squared minus y squared equals to c, that implies that 2x minus 2y dy dx is equal to 0, right? This one is nice in the sense that the parameter of the family just differentiated away. Sometimes you have to make an extra step to get rid of the c. I'll try to, the next example I work, I'll try to have that detail, okay? But I'm going to stick with this one here. But before I go further, though, what is this family? I'll do the picture over here. If c is positive, what do you have? Like x squared minus y squared equals to 1. What is that? So equal to 0 gives you what? Plus or minus x, right? Those are these guys. If in the first equation, what happens when you put x equal to 0? I get minus y squared equals to 1, which you just told me has no solution, right? I'm going to dot the axes because I want to emphasize that the axes are not part of the solution I'm graphing, okay? Right, so that means that we don't cross x equals to 0 with the 1 solution, right? In other words, it's a hyperbola which opens which way? Like this, right? That was supposed to be symmetrical. Oh well, I tried. And then, of course, the minus 1 are actually these guys up here. All right? And these guys down here. And if you go on to plus or minus 2 or plus or minus 3, you get like these, right? There's a whole family of these hyperbolas. They fill the xy plane, right? So forth. That's the family we're looking at. We want to find the orthogonal trajectories to these. So what I do is I find the differential equation that corresponds to the family. I'm almost there. dy dx equals to what? Looks like x over y, right? Now, orthogonal trajectories should do what? Should be something like this, right? The point is, where they meet, they should meet at right angles, right? The tangent line to those intersection points should be right angles. In other words, the slope of the curves should be what? They should be negative reciprocal, right? What is the slope, though? So dy dx for the orthogonal trajectory should be minus 1 over dy dx for the Pac-Man family. That's the orthogonality condition. So, in other words, I need to solve dy dx equals to minus 1 over x over y in order to find the orthogonal trajectories to this family of hyperbolas. Of course, the fraction of the fraction is just the what? Minus y over x, right? And you can do separation of variables, right? What do we get? Minus dy over y equals to dx over x. Actually, I'm going to put the minus back on the x side, if you don't mind. Now we can integrate both sides, right? This gives me log of the absolute value of y equals minus the log of the absolute value of x, which of course plus a constant, which is equal to log of x to the minus 1 power plus c. And so we get the absolute value of y is equal to e to the natural log of the absolute value of x to the minus 1 plus a constant. Cleaning that up a bit, that gives me y is equal to k divided by the absolute value of x. So, in other words, it's exactly these reciprocal function curves. So it's like y equals k over x and y equals, well, I can just express this as y equals k over x. it's a quirk of this formula, but this is the same as y equals k over x if I let k, if I just let k go through all values for positive or negative x. So these are all of these curves are covered by that. It's a quirk of this example, you know. Well, I guess it's not it's the same for the red, right? Different positive or negative values of that. Let's see here. 0, I guess the interesting thing is 0 for the red family is the asymptotes, right? Which are members of the family. But here, if you put k equals to 0, you get what? Oh, I guess you get y equals 0, don't you? Ah, cool, cool, cool. So k equals 0 is this one, isn't it? That's y equals 0. I suppose if I'm a little bit more open-minded about not thinking of x and y differently, that would also give me this, right? You can see that those do meet perpendicularly. There's one point, of course, where this breaks down, which is where? At the origin. Things are kind of screwy there. Right, well, I would say geometrically, I think they're allowed. I will agree that the calculus we're doing doesn't include them. But I think that's a shortcoming of the calculus. Sometimes calculus will miss an exceptional case like that because calculus doesn't realize that y and x are just two different labels in equally well-deserving directions in terms of geometry. Yeah.
So just because of the kind of window for
Hmm?
Is that just because we want
It's because we want y to be a function of x, but it's also because this differential equation here, right? I mean, I guess my point is, where we went wrong was up here. Going from here to here was not legitimate. Like, if I was going to be more sort of even Steven as far as the coordinates go, I would write this as the differential equation. I would put the differential equation in the so-called Pfaffian form. But now I'm telling you things that I'm not supposed to talk about in here. But this is a way of looking at the differential equation which puts x and y on equal footing. And you can see in that differential equation, if you put y0, well, I don't know, I think you can maybe see from this that if you put x equals to y, you get 0, or if you put x equal to minus y, you get 0. The orthogonal trajectory Pfaffian form is, I think, 2y dx plus 2x dy equal to 0. And if you look at that, you can see that either x equal to 0 or y equal to 0 make all of those terms be 0. And that properly includes the axes in both cases. But the cost is talking about Pfaffian forms, which I'm not supposed to talk about in here. So yes?
Isn't that if x and y is equal to 0 and y is equal to 0 are two orthogonal trajectory, isn't that it does not perpendicular to the x equal y, x equal minus y. It isn't.
Oh, right. I totally agree that the origin has to be thrown out. That is a place where they're not meeting perpendicularly, right? There's 45 degrees between the asymptotes and that. Yes, I agree. My point is, if you just get rid of the origin, everywhere else that they meet, the axes, the axes, not the origin, but the axes are okay, right? Like here, it's meeting perpendicularly. Up here, when these red lines cross the vertical blue line, they're perpendicular. Listen, let me just get to the point here, guys. What I would be looking for if I assign this problem on a test is that you find this. Right? That's the main thing. That's that describes the family of orthogonal trajectories to the given set in this case. All right, let me do another one. Oh man, you shut up. All right. if we had, how about this one? X squared, y squared equal to constant. Or, oh, no, I don't want this one. This one's no fun. What I want is y equals to mx. I'm going to give that as my initial family. So what happens is m varies. Geometrically, what is this family? Right, these are lines through the origin, right? So if we want to find the differential equation for this family, differentiate that, right? What does it give us? Right? Now here's the thing. You can't leave that m there. You have to rewrite m in terms of y and x. M is equal to y over x. Okay? So then that gives me dy dx for the orthogonal trajectory should be equal to minus 1 over y over x. In other words, I need to solve dy dx equals to minus x over y to find the orthogonal trajectories. If there's a parameter in the family of curves, you have to eliminate it before you go on from there. All right, that's what I'm trying to show. That didn't happen to us in this last example, right? Because when we differentiated the initial family equation, the level curve, the level just was gone, you know? But here I presented the problem in such a way that after we differentiated it was still there, you know? Okay, so anyway, now we solve this. We've solved this before. I'll solve it again though. So this is y dy equals minus x dx. Integrate both sides. 1/2 y squared equals minus 1/2 x squared plus a constant, aka x squared plus y squared equals to 2 times the constant, but I'll call that r squared because I think that's what you should call it. You can recognize these are these guys, right? So the orthogonal trajectories to lines going through the origin is a family of concentric circles, right? And again, there's something funny that happens at the origin, right? You know, this story kind of breaks down at the origin, doesn't it? Why do you care about orthogonal trajectories? Do you guys know? What's that? Polar, kind of like polar coordinates. Yeah, that's a good comment. These would in fact be the lines of constant theta, right? And the black ones are the radius is constant, right? So those are the polar coordinate lines. That's true. That's good. What's that?
I think that, I don't know how that edge on the end, and there's an edge too, and there's a line.
Ah, yes. Yeah, I think that's the other thing that pops out at me. Some of you guys soon take Physics 232, right? And so there you talk about the voltage, V, right? And the electric field. E, right? And in 2 dimensions, if you've got a charge Q like that, then if you've got another charge over here, Q like that, then what happens is the field lines do all kinds of crazy stuff, right? They're like, why am I doing this super complicated case? What's wrong with me? Let me stop this. What am I doing? Idiot. Coulomb field. a charge at the origin, the field lines are like this. They're symmetric in all directions, all right? Now, what do I mean by field lines? The density of the field lines you draw illustrates the magnitude. So these should be equally spaced, everything else being the same. I think I've gotten too carried away with this. All right. It's kind of like a drug. It's hard to stop once you start. I wouldn't know. Let's see here. For coffee. So these are the electric field lines. What that means is that if you pick some point in space, like say this one, right, then the electric field actually points like that. The electric field is a vector field. It fills space. Every point in space has an electric field attached to it. The electric field propagates the influence of the charge, which in this case is the origin, at the origin, to other charges out there, right? Okay, so anyway, the electric field is equal to minus the gradient of the voltage function. Now that's the three-dimensional thing, I should say, but in 2 dimensions, it just simplifies to being, well, anyway, in calculus 3, let me just say it that way, you will learn that the gradient vector points in the direction of increasing. Like, if I talk about the gradient of f, this thing points in direction in which, that's bad grammar, it points in direction for which f levels up. So in other words, if you have level curves of f, right? Level curves of f, if they look like this, then if this is the next level, then like the gradient of f is pointing that way. So it's like we had a professor who used to be here, he used to say it's kind of like a compass that always tells you to go up the hill. So that always points in the direction of leveling up. Now in this case we're in a valley, I guess, but so here, if I draw this, that's what I got to do. These are so-called equipotentials. Equipotential. In other words, the curve of constant voltage. Now there's a minus here. This pesky minus changes things up a little bit, right? That means that the electric field points what? It points in the direction of minus the gradient. In other words, the electric field points in the direction in which the voltage is decreasing. So these, as you go further and further out, we're going to lower and lower voltage circles. But the voltage, the equipotential lines and the electric field lines, they form orthogonal trajectories because the electric field and the equipotential lines are perpendicular. Again, the full story is in calculus 3, but just I can tell you that much here. Right? So that's one of the reasons we're interested in orthogonal trajectories. You will do labs about this in 232. There's some pretty neat ones. Anybody done them yet? Yeah, you've done it, Nathan, right? The silver painting. Or no, you don't do silver painting. What do you do? We used to have to paint silver paint on stuff. It was awful. I'll shut up, but yes, that's good. It's good that you don't know what I'm talking about. Do you guys have any questions about the homework? You have 10 minutes left, I suppose. All right, well, you can turn it off. I'll give you guys back your quiz. For reasons I don't